Hello everyone, welcome back. So, we have finished the discussion on the deriving the momentum equations for the general flow, which may be compressible, incompressible. So, we have found out that those equations are basically we did not consider anything about the variation in density, and we also saw that you naturally basically get a Mach number out of it, and you can see how the pressure is or the density change related to the velocity change. Okay. Now, we are going to go to derive the equation for truly incompressible flow. So, what do I mean by that? So, what I am saying is Mach number is equal to U by A. Okay. So, I am talking about true incompressible flow which does not exist. Okay. All flows have got some or other compressibility. Okay. Gases are more compressible than liquids, but even liquid has got some compressibility, but for all practical purposes you can ignore them and you can derive equations for truly incompressible flow. That means your Mach number basically tends to 0, and that means your speed of sound tends to infinity, right. So, because the speed of sound is infinity, okay, in these kind of flows, if you are assuming an incompressible fluid, okay, incompressible flow, what will happen is that if you have any change anywhere, let us say this is your computational domain, okay, and you make some change here, okay, just perturb it here, it will be immediately felt everywhere, okay, because your speed of sound is infinity. Okay. On the other hand, if the flow is compressible, you will have finite speed of sound and it will travel in a direction, in a given direction, and then it will go, I mean the information will reach with that speed of sound, right. So, because of the assumption of the flow to be incompressible, your basically discretization, your scheme to basically solve any gradient or basically your physical system, the way you basically emulate it to the numerical system changes, right. So, before we go into this incompressible flow CFD, let us try to see what are the governing equations for the incompressible flows. Okay. So, we already have the derived the compressible flow equation. Okay. So, what you can do, you can just use the assumptions that we have for the incompressible flow, and then you can basically find out the governing equations, okay, all the governing equations. So, one thing is del dot u equal to 0, that we already derived using our mass conservation law. Okay. So, we had d rho by dt plus del by del x j rho u j equal to 0, and what we did, del rho by dt plus rho del u j by del x j plus u j del rho by del x j is equal to 0. Take these two together, that becomes, this gives you d rho by dt, and what is this? This is del dot u, rho del dot u is equal to 0, right. And we said that for in a truly incompressible flow, your d rho by dt goes to 0. Why? Because your change in density is 0. Okay, the acceleration, there cannot be any change in density following a streamline. Okay, the total change in density has to be goes to 0, and that gives us the relation which is del dot u equal to 0. Okay. And what is the consequence of getting from this to this, that we lose one dynamical equation, right. What is this del dot u now? It is just a kinematic condition. Okay. This is the dynamical equation. Okay. You can solve for rho here. Okay. How the rho is changing in time, you can get that, and because we assume that rho to be constant, we ultimately get this condition which says that the divergence of velocity has to be 0 at any point in your in a incompressible flow, right. So, this we already got. Now, the second thing is to get the momentum equation. Okay. So, let us get the momentum equation. So, momentum equation we will use this condition and get this incompressible momentum equation. right. So, the momentum equation is del rho ui by del t by del xj rho ui uj will be minus del p by del xi plus del by del xj, okay, sigma ij and plus rho bi. Okay. Now, here this is general momentum equation that we have derived. Okay. And now what we are driving is making an approximation that flow is truly incompressible. So, what happens to this equation? And this was basically 2 mu Eij and minus 2 mu by 3, that was basically lambda, okay, and delta Ij Ekk, right. So, this is the expression that we have been using. Okay. So, here I am saying lambda equal to minus 2 mu by 3 using the Stokes hypothesis. So, now make assumptions where we say that the flow is truly incompressible. So, the rho can come out, it does not matter whether the rho is inside or outside, you can take it out. So, you can write it rho du by dt plus rho d by dxj, okay, ui uj, okay, it will be equal to minus dp by dxi, okay, and then you have this term d by dxj sigma ij plus rho bi. Okay. Now, since your del dot u equal to 0, okay, this term identically goes to 0, right. So, try to get this term del by del xj sigma ij, your stress term for an incompressible flow. Okay. So, that will be del by del xj 2 mu ij. So, that can be expanded here, I will write in expanded form, okay, mu, or you can take the mu also out, because see in the when we derive the compressible flow equation, the mu is inside here, because mu can also change in space for the compressible flow, right, because mu is a function of temperature. Okay. In the compressible flow the temperature changes, and because of that your viscosity may change. So, you might have different viscosity at different locations. Okay. In the case of incompressible flow, your temperature is, if the temperature is not changing, you can have incompressible flow with the Boussinesq approximation, which will probably talk later, where you might your density might be changing because of, let us say, change, you are adding some energy, you are adding some heat, right. So, in that case you may have to consider the variation in viscosity with the temperature, but you need not use the compressible equations for that those kind of flows, right. You may use the compressible, but since the change in density is due to the temperature and not due to the pressure, so those are not truly compressible flows, right. So, you can basically add some source term in your momentum equations, and you can have temperature as a passive scalar, and you can solve that problem, right. So, if the mu is not changing with temperature, you can take the mu also out here, okay, because temperature is not varying, right. So, then we will have 2 E I j is what, del u I by del x j plus del u j by del x I, okay, and then you have minus 2 by 3, and you have delta I j del dot u, right. So, this goes to 0 anyways, right, for the incompressible flow. Now, we have these terms remaining. So, mu del by del x j, and we will use both the del u I by del x j and plus del by del x j del u by del x I, right. So, then this can be written as, first part will be mu del to u I by del x j square, right, and then second term you can basically interchange it. You can take this del by del xi first, and second will become del uj by del xj. Okay, what is this? The j is a dummy index here. Okay, so this is nothing but del by del xi of del dot u, right. So this will also go to 0. And what is this part? Del to uy by del xj square. So this is nothing but, because it will repeat in j. So this will become, this is basically nothing but del to uy by del x square plus del to uy by del y square, or x1 square x2 square if you are comfortable with that, uy by del z square. It can be written as mu del square ui, right. So the entire stress term that we had, so complicated relation, we basically get it to, you can write this entire thing as mu del square ui, right. So this is the final expression that you get. Okay, if you want, if you have the body force, you can use this body force here. This can also be expressed as del uy by del t plus del by del xj uy uj will be minus del p by rho, okay, xi, okay, plus so here it will be mu, okay, this will be mu by rho, that becomes nu del square ui plus rho bi, right. So this is p by rho, okay, the pressure per unit density, okay. So this is the quantity, this is the definition of pressure in many of the solvers, okay. For example, if you are using an open form solver, so the unit of P is not the Pascal, okay, but you will have this unit which is given by P by rho, okay, that comes because of this definition. And the other reason for treating not P but P by rho is that anyway P is not a thermodynamic pressure in the incompressible flow. So that should be very clear to you, that we cannot use P equal to rho RT relation in the incompressible flow, okay. It is not valid for incompressible flows. Truly incompressible flows, okay, because your density is constant and temperature is constant, so you will not get the pressure there. The other physical aspect is that the pressure that you experience in the in an incompressible flow is a mechanical pressure. It's a purely mechanical pressure, okay. It is not the thermodynamic pressure that you basically get in the compressible flow, right. So in fact, that pressure is indeterminate in the incompressible flow. You cannot determine the absolute value pressure in an incompressible flow. What you can rather get is the pressure gradient. So in an incompressible flow, if the flow is happening, it does not matter what pressure you put here and what pressure you put here, okay. What matters is what is your dP by dx, okay, or the pressure gradient. So the pressure gradient is what determines how the flow will evolve, and you can, for the calculation purpose, you can have some values of P1 and P2, right, but those are not the absolute values. So you should not be trying to relate it with a thermodynamic pressure, okay. So now we got two relations here, okay. So the two relations are del dot u equal to 0 and the other is your expression, the momentum equation, which is given here, okay. Now what are the variables that you have that you want to solve for? Rho is a constant, so you don't need that. U, V, W and P in a 3-dimensional flow, right. But if you look at the expressions, okay, so this is your first expression which is coming from the mass conservation, and as we have been discussing, this is a kinematic condition, this is not a dynamical equation, okay, but you have 3 dynamical equations for velocity, okay. For U, V and W, you can expand it and write in x momentum, y momentum and z momentum, you can get the dynamical equation for the velocities, right. But you do not have the dynamical expression for the pressure. So how do you determine it? So that is the question, right. So the Navier-Stokes equation do not have an independent equation for pressure, okay. For compressible P is the thermodynamic pressure, as I told you, and the mass conservation equation is the dynamical equation for density. Okay. For incompressible flow, the P is a mechanical pressure. Okay. So, this is just a kinematic constant or kinematic condition on the velocity field. We do not have dynamical equation. So, how do we estimate pressure for incompressible flows? So, what we will try to do that if we do not have the equation for pressure, we will try to get an expression for pressure by using the relation which can use your kinematic constraint and your momentum equation. So, how do we do that? Okay. So, write your expression. Okay. Is equal to minus del xi p by rho plus nu del square ui, right. If you write this in vector form, so sometimes I mean I can also work it out in a tensor form, but sometimes it is easy to use the vector form because you can easily figure out. For example, if I say del dot u equal to 0, okay, you can easily figure that out, right. So, what I am going to do, I am trying to write it is vector form, which is del dot u is equal to minus grad p by rho plus nu del square u. Okay. So, this is my equation. Okay. And what is our goal? We want to find out an equation for pressure. Okay. This is what we want to get. Why? Because these are three equations for velocities in the momentum equation, and there is another expression which is the kinematic constant on velocity itself, right. So, how do we get the pressure, right? What you could do, you take a divergence of A. Okay, take the divergence of the entire equation A. So, basically what you do del dot this entire thing, right. So, what will happen, you can write this del dot u will be equal to minus del dot del p by rho plus nu del square, okay, del dot del square u, right. Okay, let me write the first term also. Okay, del dot del u by del t, right. Now, we know del dot equal to 0 and these are the linear operators. So, basically you can interchange the position. So, you can write it del by del t del dot u plus del dot u will be minus, what is this? This is del square p by rho will be, you can here also you can write del square del dot rho, you can interchange del square operator and the del operator, because del square is a linear operator and the divergence operator. So, this will go to 0 and this will also go to 0, right. So, what you will get is minus del square p is equal to rho del dot del u, or you can take the rho on the left also, it does not matter. Okay, rho is a constant. Okay, but because we have been following that. Okay, del square p by rho. Okay, so what we got from this, so this is called the pressure Poisson equation. And why we had to get this equation is because we knew the kinematic constant and velocity, but we do not have any expression for the pressure, and we need to basically get the pressure. So, we use this condition, okay, this is called as x. So, we used x in A and got this new equation. So, now this equation, the momentum equation as well as the pressure Poisson equation together can give you the solution for u, v, w and p. So, why it is called pressure Poisson equation? is because this, what is the form of this equation? This is basically del square f equal to phi, right. That is the form which is the equation of the class of Poisson equation, right. And please note that you need a special technique to solve this kind of equations, because when you try to solve this kind of problem, these are the class of elliptic problems, and basically you will get basically equations which are in implicit form, and you need an inversion matrix that becomes very expensive. So, you want to use some iterative algorithms. So, in that case you have some libraries which are developed for solving this kind of Poisson equation or Laplacian equation, right. But this is not easy to solve compared to what we have been using for the convection equation. Okay. So, we will come to this kind of problems also. This is an elliptic equation. Okay. When we come to the classification of equation, we will get back to this, that why it is challenging to solve or computationally expensive to solve these kind of elliptic equations. Okay. So, we got this pressure Poisson equation, okay, which is given here, okay, and the same thing. And then now that you have the pressure Poisson equation, okay, you can basically make use of the pressure Poisson equation to determine the correct values of velocity as well as the pressure. So, the solution is done typically in two ways. Okay. So, the first step is to solve the momentum equation. The momentum equation is already know to obtain the velocity field for a known pressure. So, you can take a pressure, okay, guess a pressure value and solve the momentum equation and get a velocity field, right, using the momentum equation. Okay. But it will not give you del dot equal to 0, okay, in the first step, right. You need to correct it. Okay. So, to correct it, what we will do, you will use the velocity. Okay. So, this is a pressure Poisson equation, for example, in 2D. Okay. Here ux is basically del u by del x, okay, and similarly uy is del u by del y, and so on and so forth, right. So, this is the equation, pressure Poisson equation for the 2D flow. And so, once you know the velocity values from a pressure which is your initial pressure, you recalculate the pressure using your pressure Poisson equation and get a new pressure, right. But when you do this, it will make sure that your divergence goes to 0, right, because while deriving this, we have ensured that del dot u goes to 0, right. So, this is the two-step process, and now you have an updated pressure. Use this new pressure to calculate the velocity again, and then use the pressure Poisson again to ensure that divergence is 0, and this process gets repeated. Okay. So, this is how you solve your incompressible flow. We will not go into the detail of solving the incompressible flow equations in this course. We will be mostly using the compressible flow solver, okay, because we want to go and deal with the problems which involve shocks and strong discontinuities. Okay. The incompressible flow cannot give you that kind of solution, right, an incompressible flow solver. So, final thing before you conclude the class today is a brief discussion between the conservation and the non-conservation form, right. So, if you recall, we had used this del rho u by del t plus del by del x j rho u I u j. So, this was your conservation form, okay, which was minus del p by del x I plus del by del x j sigma I j, okay, and plus rho b I. This is the conservation form, and you can take this rho out and use the equation of continuity to get this non-conservative form. Okay. Okay, something like this. equal to minus del p by del x I by del x a sigma is a plus rho bi. Okay, this is the non-conservation form. Okay, and this can also be written as dui by dt. Okay, the Lagrangian expression. Okay, and we had discussed that there is no difference between this form and this form. Okay, this has been obtained using directly from the conservation law, and this has been obtained by making further consideration that your del dot u goes to 0, and then we obtained this non-conservation form, and we argued that this is basically mass into acceleration, which gives you the force, right. So, if the flow is continuous and the flow is smooth, you can use either of these forms, okay, to solve the problem. But if the flow has got shocks, okay, or strong discontinuities, then you will have trouble solving using the if you use the non-conservation form. And why is that? So, what happens across a shock? For example, if this is a shock here, okay, so you will have basically you can have the change in density. Okay, so your density increases. So, rho 2 is much greater than rho 1. Your velocity decreases. Okay, u1 is much less than u2, and so on and so forth, right. So, your the primitive variables go strong change across these strong discontinuities like shocks and all, right. But your flux, okay, so which is rho u, okay. So, this you can use smoothly despite your rho decreasing rho increasing and u decreasing across a shock, you can have this conserved variables which is rho u, which can have a smooth transition across the shock, right. So, that is why using this conservative form where you are treating rho and u together is useful if you have flows have shocks, and that is why this form is basically used in compressible CFD. Okay. The other advantage of using this form is that let us try to write basically your expression using this form, and so if you have dou rho u del x, or it can be del t also. So, the left side I am writing the conservation form and right side I am using the non-conservation form, okay, right. So, this is both are equal. I have just used the chain rule, okay, but let us try to do solve this problem on the left side and right side separately, right. So, if you are using, let us say this is your grid, okay, I plus 1, I minus 1, I minus 2, I plus 2, and so on and so forth, right. So, if you use a simple differentiation scheme, whatever you have studied in your basic math course, let us say use the central differentiation scheme. So, you can write rho u I plus 1, rho u I minus 1 by 2 delta x, right. And here if you solve, so here rho, okay, u I plus 1 minus u I minus 1 by 2 delta x plus u, okay, and rho I plus 1 minus rho I minus 1 by 2 delta x, okay. So, the question is what is the value of rho you should be using, and what is the value of u should be using, whether it is I plus 1 or I minus 1 or I, what is the value that you want to use here, you can use here, okay. Similarly, for u, what is the value that is suitable for this, right. So, you will see that we will quickly run into trouble when you use this non-conservation form, and the left side is not equal to the right side in the discretized form, okay. In here it is fine, in the continuous form it is fine, in the discretized form this left is not equal to right, and you have, I mean, if when you use I plus 1 or I minus 1 on I, you may get different values. The last advantage that I want to discuss is that this, if you have like boundary to boundary, okay, this is let us say I equal to 1 to I equal to n, right. So, if you express it here, so you can have basically rho u 2 minus rho u 0, I mean you can have a ghost shell here, okay. So, this is 0 and this is n plus 1, okay, outside the boundary, okay. If you have a periodic boundary, then you can have n equal to 0 and n plus 1 equal to 1, right. So, that will be 2 delta x plus you will have rho u 3 minus rho u 1 by basically 2 delta x and so on and so forth, right. So, you can basically then you will have rho u 4 minus rho u 2 by 2 delta x and so forth, so on and so forth, right. So, if you add all of this, okay, so here for example, this rho u 2 goes to 0, right. Similarly, in the next term we will have rho u 1 going to 0 and rho u 3 going to 0 and so on and so forth, right. So, all of these terms will basically collapse and what you will have is basically in this case rho u 1 plus 1 minus rho u 0 by I mean 2 delta x, right. So, whatever flux you are getting in and getting out, you can calculate that. This can be better understood if you let us say use the one sided difference, okay, and not the central difference. Okay. So, if you do that, let me work that out. So, now what we are doing, we are using the one sided difference, okay. Yeah, del rho u by del x is equal to rho del u by del x plus u by del x. Okay. This is basically rho u I plus 1 minus rho u I by delta x, right. So, that will be basically rho u 2 minus rho u 1 by delta x plus rho u 3 minus rho u 2 by delta x, okay, plus rho u 4 minus rho u 3 by delta x, and it will keep on going till you have rho u n minus rho u n minus 1 by delta x, right. So, you can see that here your rho u 2 is getting cancelled, okay, rho u 3 is getting cancelled, and similarly rho u 4 and everything will get cancelled, okay. Here rho u n minus 1 will get cancelled and what you will get is basically rho u n minus rho u 1 by delta x, right. So, if this is your grid starting from 1 to n, right. So, you can see that all these values inside have vanished, right. So, what you have, so this is your inflow, so this is your influx and this is your outflux, right. So, outflux is rho u n and this is rho u 1, right. So, only the difference between the two is what you are getting here, right, which is expected also. Your net change is basically whatever is you are getting in and difference between the what is getting out and what is getting in, right. And this is because of your discretization. So, this is called the telescopic collapse of flux, okay. So, this will happen only when you use the conservation form, okay. If you use the non-conservation form, so if you use this expression, so let us say I am using I here, rho I del u I plus u I plus 1 minus u I by delta x, okay, plus u I rho I plus 1 minus rho I by delta x, okay. In the next case, it will be rho I plus 1 u I plus 2 minus u I plus 1 by delta x plus u I plus 1 rho I plus 1 I plus 2 rho I minus 1 I plus 1 by delta x and so on and so forth, right. It will go till the end. So, here because I mean here I have used the point, this is I, this is I plus 1 and this is I minus 1. So, while calculating the derivative I use the value I here for rho and u, okay, when you are calculating the derivative at that point, but you can use I plus 1 also as you have discussed earlier, right. So, that was one issue, that what value you should select for these different variables. The other issue is that when you sum this up, this will not lead to the telescopic collapse of flux, okay. So, you will have some differences, okay, between the value that you are getting here and when you are calculating the value here, right. So, that is another disadvantage of using the non-conservation form. So, with that we will finish the class today, and we will be using the conservation form for our CFD calculation, because we are dealing with the compressible flow CFD, and we will write all these expression in the matrix form. But before that, there is another conservation that is important that we need to deal with, that is the energy conservation, okay. So, in the next class we will finish the energy conservation, okay. Then we will cast all these equations in a nice way, in a matrix form, and then we start solving those problems, okay, flow problems. Thank you very much.